introduction about myself. I'm lead scientist and a product manager here at Anton Paar Quantitech. Quantitech is one of Anton Paar's manufacturing subsidiaries, formerly known as Quantachrome Instruments, and that name might be familiar to some of you. I've been with Quantachrome and Quantitech for 30 years now, and in the field of porous materials characterization and porous materials in general. I have 10 patents in that, and I'm co-author of Characterization of Porous Solids and Powders, Surface Area, Pore Size and Density by Springer. So if anybody's interested in more details on the characterization of porous materials, by all means, have a look at that. But today, what I'm going to focus on is, as Mohammed introduced, core analysis by Poremaster. Poremaster is our mercury intrusion porosimeter, our tabletop device. And today's agenda, I'll go through an introduction to mercury intrusion porosimetry, so get everybody up to speed on that. Then I'll give you an overview of the Poremaster instrument itself. I'll include a software demonstration to show you how we make an analysis on the Poremaster and how we look at the data. And then I'll give you some examples of what some of our customers have been able to achieve using the Poremaster when it comes to core analysis. And then hopefully we'll have some time at the end for questions. We did allow quite a time slot for this, so we should have plenty of time, hopefully. So let me start with an introduction to mercury porosimetry. So the aim, obviously, of making these measurements is to measure the pore size and pore volume distribution in porous materials, including rock cores. So we usually call this a pore size distribution. What that means is how the pore volume is distributed amongst pores of different size. Now, this technique basically has a unique capability amongst all pore sizing techniques, in that it has an extremely wide dynamic range of pore size from around about a millimeter. The exact size depends on the contact angle that the liquid metal makes with your sample. But from about as large as about a millimeter down to as small as 3.5 nanometers, there or thereabouts. So a very wide dynamic range. And this whole process of being able to measure pores by this method relies on the non-wetting behavior of a liquid, in this case, liquid mercury, on the solid. So the graphic here basically just shows what happens when you have a wetting liquid, contact angle less than 90 degrees, then we get spontaneous, what is called capillary rise. The liquid has a higher affinity for the walls of the capillary than it does for itself. So it spontaneously will move into the pore system. Conversely, a non-wetting liquid likes itself greater than it likes the surface of the capillary. So the cohesive forces, if you like, are higher than the adhesive forces. So it doesn't want to reside in the capillaries at all. It wants to be outside the capillary. And depending on the size of the capillary or pore, will determine the degree to which it will dislike that pore. So the smaller the pore, the more it dislikes being in that pore. And in order to move mercury into smaller and smaller pores, we have to apply higher and higher pressure. So as we'll see, mercury porosimetry is basically a pressure technique of forcing non-wetting liquid into the pores. And you say, well, this must be, a very modern technique. But in fact, it was first proposed in 1921, this whole concept. Now, what they could do in 1921 is very different than what we can do today. But last year, we celebrated the centenary of this proposal. The idea of pushing mercury into a porous solid to measure pore size and to measure pore volume was originally proposed by E.W. Washburn in 1921 in a very short communication, less than a page of text in that particular journal where he published. And basically, he said, well, look, using this equation, which for those of you, who've done a little bit of physics maybe, or physical chemistry, and maybe some other engineering considerations, this is actually really nothing more than the Young-Laplace equation. In gas sorption, we refer to it as the Kelvin equation. But we give credit to Washburn in this context, measuring pore size by mercury, and we call it the Washburn equation. So it's a very simple concept. If we know the surface tension of the mercury, that's gamma in this, and the contact angle of mercury on a solid, and we take the cosine of that. Generally, we take 140 degrees to be the contact angle of mercury on almost all solids. That's the IUPAC recommended value. That's the International Union of Pure and Applied Chemistry. If you look at standard reference materials, 140 degrees is also the angle there. So if we measure pressure at which mercury is forced into pores, we can calculate the pore diameter using this very simple Washburn equation, the Young-Laplace equation. So a very simple principle. Engineering is a different matter. To be able to do this safely and accurately and with a great deal of sensitivity. So I did mention that the technique as a whole has a very wide pore size capability, and we generally refer to that as the meso-macro pore range. So mesopores are everything from 2 nanometers to 50 nanometers, according to the IUPAC definition. So if you remember, I said that mercury porosimetry as a technique can go down to about 3.5 nanometers. The limitation there is the highest pressure that we can generate in this technique, which is about 60,000 psi, 4,000 atmospheres. And that'll get us down to about 3.5 nanometers. So mercury porosimetry can't get us into the very smallest of the mesopores, nor can it tell us anything about the micropores in the sample, which according to the IUPAC definition is everything smaller than 2 nanometers. To do measurements below 2 nanometers, we would use gas sorption as a technique. And there are indeed some applications for gas sorption in rock core analysis, particularly in the shale end of things. Perhaps not so much in the sandstone end of things, but certainly in the shales, gas sorption plays a significant role in that. On the macro pore side, IUPAC says everything larger than 50 nanometers is a macropore. There's no further delineation according to IUPAC. Now, if you're interested in nanomaterials generally, and say, well, maybe my rock cores have some nanopores. The general description of nano is everything smaller than 100 nanometers. So smaller than 100 nanometers, yes, we can refer to those as nanopores, which includes 50 nanometers worth of macropores and all of the mesopore range. So this is the range that we're covering. And again, it's a very wide dynamic range. So just to put it into context, that the technique is not sort of application specific. It's a very widely applied method and is applicable to basically all those materials that have pores within this range. And obviously today I'm going to look at core samples, so geological samples, which, mostly for oil and gas reservoir rocks, for example. But other, geological systems are, might be of interest as well. But just to put it into context, once you've got, oil and gas out of the ground and it goes down the, downstream processes, and we end up with useful products out of it, along the way, it might be that catalysts, heterogeneous catalysts, petrochemical catalysts are used. And this technique is extremely widely used for characterizing heterogeneous catalysts in the petrochemical field, Also in the non-petrochem field, things like ammonia synthesis. And then if you want to take from, oil and gas from, ground to end use, we pick up an application for automotive catalysts as well. So even when petroleum gasoline gets into the automobile, we have an interest to characterize pores on those catalysts as well. Various ceramics, technical and electronic ceramics are often characterized by mercury porosity. And just to round out batteries, very up-to-date application, battery materials characterized by this technique as well, and simple building materials, concrete and brick. So for example, if you're interested in the porosity of cement, for example, that can be analyzed by this technique as well. So anything where the pores lie in this range. And so just as a reminder, the maximum pressure that we can generate for this technique is 60,000 pounds per square inch, 4,000 atmospheres, 414 megapascals, and that will allow us to get into pores as small as about 3.5 nanometers, 3.6 nanometers, and the largest technique depends on the lowest filling pressure, almost a millimeter. So when we're measuring porous materials, we just have to make sure we have the correct expectations as to what a technique like this can actually perform. I also I mentioned that the largest pore size that we can measure is limited by the lowest pressure attainable. I'll define what I mean by lowest filling pressure shortly, but basically that's the starting pressure. And by filling pressure, that's the pressure at which the sample holder is filled with the mercury. I'll show you that in a little bit more detail later. And the smallest pore size, as I said, is limited by the highest pressure achievable. But perhaps more importantly, or just as importantly on this graphic on the left-hand side, is what pores can we measure by this technique? So mercury porosity can measure all of the pore size and all of the pore volume that is communicates with the surface. So the mercury, because it's non-wetting, starts out outside the pore system, and then as pressure is applied, it is forced into the pore system. So if it connects to the surface, it can be intruded by mercury, so long as along the way there is no constriction smaller than 3.5 nanometers. Okay, so let me just give you an example. Hopefully you can see my mouse. If I concentrate on this region, this uppermost region of this particle, there's a big pore opening here. So this will start to intrude at relatively low pressure because it's large. And then the mercury will basically at that pressure will stop around this region because now it's encountered a smaller opening. And in order for the mercury to move into this region, we'll have to push a little bit harder until it gets to this next smaller region. We'll have to push a little bit harder. Now, let's look at these small pores here on this uppermost surface. Now, these are really small. So when the analysis starts, mercury will not penetrate into these pores. They connect with the surface of the solid, but they're too small at the starting pressures. So they will not intrude until so much high pressure. But let's just follow where this pore network goes. And we find that on the far side of this pore network, everything else is larger. Okay, so in fact, the very smallest part of this pores here on this edge will not be intruded, penetrated by mercury from the outside, but will be penetrated by mercury which moved through this channel already because everything this way was already larger. So the pore size distribution that we measure is sensitive to the entire network, how the pores are connected, whether larger pores are behind smaller pores. And I'll draw your attention then to this pore body, more or less in the center of the particle here, which is only accessible through, well, we have to find a connection to the outside world, these 3 pores here. So this larger pore space is only accessible through small, narrower channels, narrower channel, narrower channel, narrower channels. Okay, so this is called the pore throat. In your application, it's called the pore throat. So what we measure by mercury porosimetry in rocks is a pore throat distribution. Okay, specifically the throat size. We get the volume of everything, and we can, in certain circumstances, deduce the size of the pore bodies. If I call this a throat or neck, this is the body. Okay, so sometimes we refer to ink bottle pores with narrow neck, wide body. So once mercury is filled into this, let's have a look at what's beyond it. Okay, this is what's called a blind pore. We have a whole network of blind pores down here. These too will be intruded so long as we can achieve a pressure which is high enough to push mercury through a neck. So here, again, there's another narrowing here. And these pores just narrow. See here, there's a incredibly small. This might not be, if it's small enough, this might not be intruded by mercury. There are 3 pores on this particle which cannot be measured by mercury porosimetry, and these are these closed pores that have no connection to the rest of the network, no connection to the outside world. So this is a very important concept in order to understand what it is we're looking at when we get data. And of course, it's very important to understand that we're measuring pore throat distributions and the volume of pores beyond those restrictions. So we always want to think of these pore sizes that we're measuring and pore throats as restrictions, because when it comes to oil recovery, then the oil has to migrate through the pore structure. So when the mathematical modeling is done, where do you start? Well, oftentimes you start with the mercury porosimetry pore size distribution, the pore throat distribution, in order to calculate not only what the reservoir volume is, but how the oil is going to get out. The oil is going to get out of the rock or be displaced out of the rock by basically backtracking the route that the mercury took to get in. Okay, so this is why it's so important to make these measurements to understand reservoir rock. So just briefly to describe the whole procedure of making mercury porosimetry measurement. We need a special sample cell to hold the sample. Those sample cells are called penetrometers because they allow us to measure the volume of mercury which penetrates the pore structure. The sample cell with a sample in it has to be evacuated to remove air from the inside of the sample cell and from all of the pores. And this is a programmable feature. I'll show you that in terms of how long it might take to evacuate a sample. A lot will depend on how large your sample is and how tight the pore structure in your sample it is. And then the instrument, the Poremaster, has to transfer the liquid mercury into the sample cell. That's something that the mercury does. It's not something that the operator has to do. It's not like filling a graduated cylinder or a burette with a liquid. There is a mercury reservoir, and the instrument will automatically fill the sample cell with the mercury. And then the instrument will increase the pressure, basically over the mercury and around the sample cell, and we'll start to increase that according to some protocol. I'll describe that later, in order to push mercury into whatever pores are available up to as high as 60,000 psi. Now, depending on your material, it might be that all of the pores of the particular sample have been intruded by, let's say, 40,000 psi. So there's no need to go to 60,000 psi always. It really depends on the type of sample that you have. If you have pores that are no smaller than 6 nanometers, then 33,000 psi would be suitable. And we have two types of Poremaster, one that goes to 60,000 psi and one that goes to 33,000 psi. So when you double the pressure, you halve the size of the smallest pore that's measurable. And then along the way, the instrument measures the change in mercury volume as a function of applied pressure. So it's going to track how much mercury is pushed into the sample. So what is a sample cell, this penetrometer? It's a glass sample holder that has a wide portion at the top to accommodate your sample and a capillary stem. And this capillary stem becomes the measurement capability of the instrument. It's along this capillary that starts out filled with mercury. It's along which the instrument can measure how much mercury moves into the pores of the sample. You'll be able to see a real sample cell later on when I move over to videoing the equipment. Now, this capillary stem, the internal diameter determines the resolution. So the narrower the stem, the greater the distance this mercury meniscus will move when mercury is pushed into the sample. Okay, it will move in here further for any given volume. So for low porosity, we have one sample cell that has a total intrusion capacity of 0.5 cubic centimeters. For higher porosity rocks, we have a penetrometer with a stem that has a 2 cubic centimeter intrusion capacity. Now, the other variable here to make sure that we're making most of the instrument resolution is to increase or decrease the sample volume here. So, you know, if we want to have more pore volume for the instrument to measure, we can use a larger sample. If we have a very high pore volume, we can afford to use less sample. So this bulbs part of the sample cell, we have different types of sample holders to accommodate larger samples or smaller samples. And in the examples I'll give you later on, some of our customers have used very large capacity sample cells and some have used the smaller capacity sample cells. So we have the ability to measure up to a 1-inch core plug sample down to much smaller pieces. You know, with a mind to, you know, using liquid mercury, if we can, or, you know, if you're using this technique, if you can minimize the amount of mercury that's used, then that's good for operating costs and obviously good for the environment. There's less mercury that has to go into the recycle system. We never, you know, blindly dispose of mercury. It has to go into a recycle route, and then it's redistilled and you buy it back fresh. We always want to use fresh mercury for these measurements to get high quality analysis. If you are working with powders, we have to take care to not lose powder particles out of the stem, and we have sample cells that will mostly minimize the risk of losing powder out of the sample cell. And then the analysis is actually a two-stage process, what's called a low pressure and a high pressure process. And I'll be able to describe to you that later. And as I'll show on the instrument, the sample cell is filled in a near horizontal position as you see it here. It's not filled in a vertical position. Filling it in this orientation allows us to measure a as large a pore size as we can by this technique. So this is the macro cell shown here, and it has a large capacity here, which it can accommodate up to a 1-inch diameter plug, up to about 30 millimeters long here. Now, if you don't have to analyze this type of sample, you can analyze smaller samples, things like, you know, cuttings, for example, You don't have to use a large cell and fill this with a lot of cuttings. I mean, by all means, you can do that. This is designed for the cylindrical plugs, or you can use smaller sample cells for smaller particles, smaller cuttings, for example. So these types of sample cells can accommodate, there's actually two types, up to 8 millimeters, and then there's a slightly larger one up to 10 millimeters, 1 centimeter across. So these are generally the type that what one would use for cuttings, for example, and this is the one that you would use for actual core plugs. So once you have your sample cell in there, the sample goes in this end, and then it has to be closed off, and then the instrument will add mercury from the open stem end. And when the sample cell is put together, I'll show you later live, it's capped off with a metal disc, and this allows the instrument to make electrical contact with the mercury that's filling the sample cell. Okay, so this is more or less what it's going to look like when it's assembled. There's a grease seal here, which is makes a vacuum tight seal, and then there are two plastic pieces which screw together to hold the cap on. And again, I'll show you that later. Now, once the sample is in the sample holder and the sample holder is in the instrument, it's going to follow this process. Hopefully this will work. So basically, the mercury is filling the stem, and in this case, I'm showing some discrete particles. These might be cuttings, for example. And at the starting position, maybe the mercury didn't even fill all the spaces between the cuttings. Or if this were a powder material, then these would be the interparticle voids between all the powder particles. Now, this stem here serves as what I like to describe as an electronic burette. So the instrument can follow the movement of mercury out of the stem as the mercury moves into the pores. And I say, hopefully this will work. Sometimes this animation works, sometimes it doesn't. Okay, so in order to make an electronic burette, we put a metal cylinder around it. So we can make capacitance measurements, which measures basically the length of this mercury column. And as pressure is increased and smaller pores are penetrated inside the sample, so the mercury moves out of this capillary stem. So in terms of measurement science, the mercury constitutes one plate of a electronic capacitor, and this metal cylinder is the other. I'll show you this again on camera shortly. So the intrusion of mercury is recorded as pressure is applied, obviously with much greater resolution than I showed here. Now, just to again show you how everything is going to proceed here. So pores of decreasing size are filled in order as the pressure on the mercury is increased. So in this, and this is a very simple pore network, the largest pore, which communicates with the surface, will be intruded first. And this just intrudes at one end. Okay, so it's only connected at this surface. And then the next size 2, then 3. Now, pore 3, okay, can intrude from this face, but will also be filled through pore 2, okay? Because now at that point, both ends would be in contact with mercury, and so on. So it proceeds with 4 and then 5. So if you look at this pore 4, this is an ink bottle pore, and this is why we call this pore throat measurement. So this pore, you say, well, this is not the same pore as this one. In terms of how the mercury will fill this space, it is. So when the pressure is high enough to fill a pore of this diameter, it will fill through here. And then because this is a larger diameter, it will just continue to fill this whole volume. So this volume is associated with this pore throat. And this is the important concept. So this is our expectation, that we're measuring pore throat distributions, the volume of the throat and the volume of pores beyond the throat. So it's a very important concept to have in mind when it comes to looking at the data. So just as a matter of review then, we measure this. What the instrument is basically measuring then is capacitance of this electrical circuit, okay? And then that capacitance is converted to voltage, and voltage is converted to volume. So if you remember, what the instrument is measuring here is the distance along which the mercury meniscus traveled. So it can say, oh, I have a high capacitance reading. It's going to get smaller, smaller, smaller. So what it's really measuring is the distance that mercury travels. I say, well, I want a volume. How do I get a volume? Well, if we know distance, okay, length, and we know the internal diameter of the penetrometer, we can know what volume is intruded. In actual fact, when the instruments are calibrated, we do a direct volume calibration to arrive at this conversion factor. So every or each of the sample cell sizes, the half cc and the 2 cc, they have different conversion factors. Now, what I show here then is the raw data, which is what we call an intrusion curve. And what we end up with here, for example, is an intrusion curve. When all of the pores are filled, then we see a plateau in the system. And then it's normal to reduce the pressure on the system. Okay, and because mercury is non-wetting, at some point we might achieve a pressure which is low enough that allows the mercury to spontaneously leave the pore system. It comes back out. Now, it does so with hysteresis. Okay, so the pressure at which mercury moves in and moves out are not the same. Now, there's some different reasons for this. One is a change in dynamic contact angle. That is the contact angle with which the mercury moves into the pore, okay, and the contact angle that the mercury makes when it moves out. So in contact angle science, if you like, during intrusion, we have what's called an advancing contact angle. And during extrusion, depressurization, we have what's called a receding contact angle. And they can be different by, let's say, 20 degrees. We do our pore throat measurements on the intrusion data, but this hysteresis is also reflective not only of a change in contact angle, but also some pore network behavior, the connectivity. The biggest indicator of pore network and ink bottle behavior, narrow necks, wide bodies, is this entrapment phenomenon. So not all the mercury that was pushed into the sample spontaneously leaves. So there will always be some mercury left behind in the pore structure. And this is, again, a characteristic then of the network. So it's sort of, empirical. It's quantitative in terms of the amount of volume, but in terms of what the pore structure exactly is, it's more empirical, qualitative indication. But again, it's important information. If two samples look pretty much the same according to the intrusion curve, you can say, the pore throat sizes are the same, but let's say you get more or less entrapment, that would suggest a different network and different sizes of pore bodies beyond those narrow necks. And then once we have the raw data, then the software converts the intrusion curve to the pore throat distribution So we get a cumulative pore size distribution, and we calculate the first derivative of that so we can get our pore size distribution. So that's what we hope to end up with. And so now I want to draw attention to the instrument itself, the Poremaster, and just to go over some of the features. So there is a very strong emphasis on mercury safety above all else, more important than the results, basically. And I'll go over some of the details of that. It is a benchtop device, so we're talking about benchtop mercury porosimetry. So when I say benchtop, it can be on an open bench so long as you take sufficient care, and I'll go over that in the mercury safety. I'll go over some of the convenience features and the flexible programming I'll do in a short software demonstration as well. So in terms of safety, which we take very seriously, basically the low pressure part of the system, this is where the sample cell is evacuated, where the instrument will fill it with mercury, and where it will make pore size measurements up to about 3.5 atmospheres pressure, 50 psi. Okay. After the low pressure has been performed, then the sample cell, the operator transfers the sample cell from the low pressure system into the high pressure cavity here. And then this will run from atmospheric pressure all the way up to maximum pressure. So it's a two-stage process. But the first stage process is, apart from putting the sample cell in and taking the sample cell out, is done behind closed doors here. Okay. There are interlock safety covers. I'll show you that live again. Because the system is going to pressurize the sample cell to 3.5 bar pressure here, it's very important that that sample cell be securely held in place. And so we have an interlocked security system there that has to be engaged before the system will pressurize those sample cells. As I said before, the filling is done automatically. There's a large capacity, easy accessible mercury reservoir here that lives behind the doors. There's an internal drip tray. Were there an inadvertent, accidental spill of a little bit of mercury, there's an internal drip tray inside this whole compartment here. So there should be no risk of it leaving the instrument. But obviously we always want the operator to work cleanly and safely. If you want to use it on a benchtop, there is an optional exhaust fan that fits in the back. It's factory installed if you want that, and that will create a constant flow of air through the instrument, pulling air away from the operator through the instrument, through the back. So if there were any mercury vapor in the instrument, it will be constantly diluted and constantly exhausted out the back, which obviously we suggest be taken to an adjacent fume hood. Okay, you always need to operate these instruments next to a fume hood. For sample penetrometer cleanup, you've got to separate your sample from the mercury, recover the mercury, separate the waste samples. That has to be disposed of safely through the appropriate hazmat disposal route. Okay, so used samples just don't simply go in the trash. They have to be disposed of safely and responsibly. But so this can sit next to an instrument and have the exhaust ducted to the fume hood. Or if your fume hood is deep enough, it can be housed completely within a suitably sized fume hood. So the whole instrument can be inside a fume hood if that's your preference, but it does have to be deep enough. The other feature on here, there's a cold trap that we normally like to use. The system, because it's evacuating the sample cell, has to pull a vacuum over mercury. And so there's going to be some mercury vapor that wants to go to the vacuum pump. So to stop that from contaminating the vacuum pump, We like customers to use the cold trap, which will freeze the mercury vapor out, so that mercury vapor will not get past the cold trap and into the vacuum pump. But there's another feature that is not a safety related feature, but it's a really useful feature when it comes to measuring the sample. And that is that the cold trap will condense out any condensables, vapors in the system. So the first one is moisture in the air. When you put your sample cell in here, sample is in the sample cell, you put the sample cell in the instrument. The sample cell and the pores of the sample are filled with atmospheric gases, which has some moisture in it, and this cold trap will freeze those out. So it improves the vacuum performance significantly. Now, it's so efficient that some people will analyze their samples as is, as received, okay, without any pre-drying. So this is a choice that you have. You can pre-dry your sample, or you can not pre-dry your sample. So if you don't, in either case, the cold trap will hasten the evacuation. It will deepen the vacuum. It will allow a much more consistent starting pressure as well. So the other convenience that we have here, I mentioned this is the low pressure portion of the instrument. This is the high pressure portion of the instrument. The instrument can operate low pressure and high pressure simultaneously. That doesn't mean they have to be started at the same time. They can be, the low pressure can be started. And normally when you start, you'll have nothing else to do except analyze the sample in the low pressure, put it in the high pressure. You can start the high pressure, then you can start the next low pressure sample. Okay, so these will run simultaneously. As I said, the evacuation and filling is automatic. So the only time that the operator has to basically, transfer mercury to anything is to fill the reservoir here. And don't forget, this will be done with this door closed, the front door open. And with the vent attached, there will be a constant flow of air away from the operator, carrying any mercury vapors to the back of the instrument and be safely exhausted. Now, when it comes to putting the sample in the high pressure system, my analogy to this are the brakes on your car. This is a hydraulic system. So the low pressure is a pneumatic system. It uses gas pressure. The high pressure uses oil. It's an oil hydraulic system. It uses a high pressure, an oil based high pressure generator. And in order to successfully build pressure in a hydraulic system, we have to get the air out of the system. Okay. So how do you have to bleed the system, like bleeding the brakes in your car. So the Poremaster has an automatic air bleed system. It has more than a single feature in it. The first one is the oil reservoir here. Okay, it's basically the bottle that the oil comes in. It's a special oil. And when it comes time to swap it out, you just swap the whole bottle out. Okay, take the old bottle out, put the new bottle in. The instrument, the Poremaster, pumps the oil from the reservoir with a built-in electric oil pump through the high pressure cavity, displacing the air that's necessarily in this cavity when the sample cell is put inside. It pushes the air out of the top through a built-in solenoid vent valve. So that's opened electronically and it's closed automatically when the analysis starts. The excess oil comes down back through a filter and is returned to the reservoir. So the operator never has to pour oil, adjust the oil level, manually bleed the system. It's a completely automatic system, but it is an essential part of high quality data. We can't get high quality data if we leave air in the hydraulic system. But once the operator presses start, everything is done by the instrument. So I'll show you the software later, but in terms of the convenience in the software and in terms of what it means for running the instrument, not looking at the data, which we'll look at later, There are basically three ways to do high pressure intrusion on this instrument. There's what's called fixed speed. It's programmable by the user. So basically the pressure generator goes slowly at a constant rate, constant motor speed. We don't use a pressure intensifier. We just use a geared down motor to force a piston into an oil cylinder and transfer pressure that way. So it's not an oil pump or intensifier. It is a single stroke cylinder that's driven by a motor. And that can be done at a fixed speed, yet, you know, you can choose whether to go slowly or go quickly. That'll allow you to look at, you know, a quick run, so you can get a fast analysis if you allow the instrument to go as fast as possible. Okay, or you can slow it down and get more resolution, allow time for the mercury to move through the sample. Okay, we can do it stepwise, so that basically instructs the instrument to go to some target pressure and then wait for some time to allow the mercury to move in. And that can be useful during in tight rocks. And if you have a core plug, which is large, 25 millimeters diameter, 25 or 30 millimeters long, compared to the size of the pores, my goodness, those pores are really, really long, right? But the question then is, well, what pressure should I ask it to measure at? How many pressure points? 10, 100? What pressures? So if you have not analyzed a previous sample, we don't really know where the mercury will intrude, what pressure the mercury will intrude, if it's an unknown sample. So we can use a variation on fixed speed, which is variable speed, which is we call auto speed, which is sample responsive. So when there is no mercury being intruded into the sample, the motor speed will run at the maximum value the user sets. Again, that could be slow or it could be fast. When the mercury starts to move into the pores because a sufficiently high pressure has been achieved, then the motor will slow down to allow time for mercury to move in. And then when the pores are filled and the instrument says, I don't see any more mercury being intruded, it will speed up again to save time. And so this system is sample responsive. Okay, so you can safely run unknown samples and still get very high resolution data where you need the data points, where the intrusion comes along. And then whatever's happening in low pressure and high pressure, on screen in the software, you'll see real-time graphical data, volume versus pressure on screen. You'll actually see that coming through on the screen, so you can watch the intrusion process. And then after all the data has been acquired, you've got extensive graphing and tabulating data, and you can set the software up to auto print a customizable report. So as soon as the analysis is over, if you have a printer attached to your PC, you can get a paper printout automatically at the end of the analysis, however many tables and graphs you want. So now I'm going to switch over to the instrument. So just bear with me while I turn my camera on, and you should be able to see part of the instrument, hopefully. I can see a little thumbnail. I'm just wondering if I stop sharing, that might be easier for you to see the video. Hopefully you can see it. So this is a live video. So I'm just going to show you some of the features. So this is the Poremaster, and this is a low pressure station here behind the door. So also on this instrument, I've had my colleagues remove some of the internal paneling here, so we can see a little bit more of the features. So this is the front door behind which the mercury reservoir sits, and so when you're filling mercury, it's only this door that needs to be open, so it contains the vapors really, really well. When you're working with the low pressure stations, this flap would be down, but I have had a cover removed here so we can see some of the safety features here. The first one I want to show you is this interlock system. So there are micro switches here, and the system has to be engaged with this micro switch here. These are bayonet, what are called bayonet fittings, and these secure. This is part of the sample cell holder. I'll show you that completed in a moment. And this has to be in this position, so the sample cell will not be cannot be removed at this point, but it must be in this position to run. Also on this display of this view here, this is a mercury overfill sensor here. We are pulling vacuum on the system, and mercury is filled up to this level. And this is an overfill sensor which stops mercury going any further than this point. This is not the normal fill level. The normal fill level here is set here, but this is a low pressure system. Now, to put the sample cell together, I promised I'd show you this. This is the a macro, what we call a macro cell. It has the capacity for a 1-inch. Maybe show you that a bit closer. A 1-inch cylinder, core cylinder. Okay, this is the stem, along which the instrument senses how much mercury is moving in. Once the sample is added to the cell, then we put on a metal cap. Sorry, a metal cap. We just use some simple vacuum grease here to make a vacuum tight seal. And then to hold that in place, we have, let me just, two plastic rings. So there's a plastic ring goes on the bottom, plastic ring goes on top. And this is simply just tightened down to hold that electrode in place. So that's what we call a penetrometer assembly now, sample inside, and that's going to go into the low pressure side of the instrument. It's going to be simply inserted like that. It's going to be tightened up. There's an O-ring seal here, and it's this O-ring seal that seals the penetrometer into the instrument. And then I'm going to put on the rest of the retaining system and makes electrical contact. So we're just going to put that on there. Just have to step up here, see what I can, so I can see exactly what it is I'm doing. And then this is going to be screwed into place here. So you can this assembly here holds the sample cell into the instrument, because don't forget, we're going to go to 3.5 bar here, and then if you remember, the mercury in the stem of the penetrometer is in contact with that metal plate on the penetrometer, which we call an electrode, and it forms part of an electrical circuit when I attach this, excuse me, okay, to that. So that's now the sample cell in the low pressure system. Close the door, start the software, and let the instrument do its thing. It will evacuate, fill with mercury, and do the low pressure analysis. Okay. Because of that hysteresis, or more specifically, the entrapment of mercury, if in the low pressure system some mercury is intruded, and then when it comes back to atmospheric pressure, some of the mercury comes back out, it extrudes back out, but not all of it, the instrument can refill the penetrometer stem. So we can always have the maximum capacity, measurement capacity for volume in the high pressure system. So what I mean by this is, if after the analysis, so the mercury starts up here, right, when it's full. So in the low pressure system, maybe some mercury is intruded, but maybe it only extrudes back to this far. So we have this much mercury unused or used up, okay, the instrument can refill this automatically. So when the sample cell goes into the high pressure system, now we have all of this volume available. Okay, and you'll notice that this is a completely glass sample cell, so you can inspect, how clean this is. If there are any breaks in the mercury column, if the sample wasn't evacuated sufficiently, it is possible to end up with some bubbles in here. Okay, and so you can actually see that and say, oh wow, let me do that again because I've got some bubbles in here. If there's a break in the mercury column in this capillary, then that basically makes the measurement not valid. And then after the low pressure run, the sample cell is going to go into the high pressure, which is this cavity up here. I'm pointing over here. And I'll show you here. This is how we make the capacitance measurements in the high pressure system with this removable sheath. We call this a metal sheath. It's a metal tube. It goes over the sample cell and allows the then in the high pressure system to measure the mercury intrusion. The low pressure sheath is built into the low pressure station. The high pressure one is different because we have different sample cells to accommodate in the high pressure chamber. The geometry is a little bit different between high pressure and low pressure. So once this has been measured in the low pressure system, then it's transferred into the high pressure cavity over here. Let me just drop that down there. That's going to sit down in here. Okay, and then this, let me just see if I can raise that up for you. This we call it a high pressure sealing plug, is going to come down and screw into the high pressure cavity and seal that up. So that seal is good for up to 60,000 psi. So that's just a quick overview of the physics of the physical layout of the instrument. Low pressure down here, high pressure up here. So the operator loads a sample into the sample cell at a low pressure. I'll show you the programming of the low pressure and then into the high pressure when the low pressure is done. So I'm just going to move back and share my screen once again and turn the camera off. So I believe you are seeing the screen that we were seeing originally. So what I want now to do is to look at the software, quick view of that, analysis setup, how a low pressure run sort of is programmed, how the high pressure is programmed, and then look at some data review and reporting and some examples what our customers have been doing. So the next thing I need to do is to start the program. That's interesting. Okay, hopefully you can see what we call the splash screen there. So to start a low pressure analysis, we can just go over here, and I've already got entered in here some sample information. For example, it might be a Berea sandstone, demo, my name. We weigh the sample and put in the sample weight. Now, when we start this, this might be completely blank, of course. Okay, this might be completely blank. And to start a standard run, I pull up a protocol and it will fill in some of the details. It will fill in the actual analytical protocol as well in terms of what analysis I want to do. It's a low pressure with refill. I can define the pressure at which the penetrometer is filled, the maximum pressure I want to go to. Do I want to measure only intrusion? Do I care about extrusion? If I don't, I just choose intrusion. I can choose how to evacuate the sample. If it's a core sample, I evacuate quickly. If it's a powder sample, I evacuate slowly. So these are all part of a standard protocol that I can create and save and use over and over again. Okay. So once all this is loaded and this sample is in the instrument, if I were connected to the instrument, which I'm not today, I'd be able to just start the analysis here. I can just start the analysis, clicking this button down here. So in terms of, this is like sample information, penetrometer information. This is the actual conditions for doing what's called a low pressure analysis, and that will create data in the low pressure region. Okay. When that's done, say, okay, I'm done with low pressure. Now I want to run high pressure. Okay. So say, and I just have some just some like non-zero values in here. Say, what I really want to do now, I'm looking at this as a high pressure. Remember, low pressure is analyzed. I've moved the sample from the low pressure station into the high pressure station. I want to run that sample in the high pressure station. So I want to transfer the information from there. And now all the information I had for that sample in the low pressure is already here. Okay. So I have all my information here. Ultimately, what I would want to do is to merge the low pressure data and the high pressure data. If the low pressure data includes some useful pore size information, I want to merge that with the high pressure data, and in which case I would choose to merge the data and choose the appropriate low pressure data. Okay, so now it's going to fill in that information. Okay, you see how it pulled in some different information. Okay, I set it back to that one. Now, the other important thing about I talked about in high pressure is how to run it. These are the 3 ways to run high pressure. Fixed rate. Okay, slow, fast. Fast saves time, maybe loses some resolution. Okay, you can end up with slightly shifted pore size distributions because of the time that it takes mercury to move through some pore networks. Okay, not every pore network, some of them. If you say, I like the idea of the instrument sort of working as automatically as it can, I will make it sample responsive, which is auto speed. Again, I have control over the maximum motor speed. Okay, here. And again, if I only want to look at a certain restricted pore size range, I can define the starting pressure. I can define the ending pressure. So here, this example, it's set to 5,000. I say, no, I want to go to 60,000. Then I set that pressure here. And anything that I create here, I can save as a high pressure protocol and just use it over and over again. I can choose only to take data on intrusion. If I'm interested in the extrusion data, I can take that. And if you've done extrusion, you can actually ask it to do a repeat up down as well, to look to see if the entrapment is reproducible. Okay. So this really all there is. Now, if you go to stepwise, then yes, you have to define the data points. You have to define the data points and how long to wait. So, for example, over here, you can define the range by pressure or by pore diameter. So if I start, I can say, for example, from 20 to 200 psi, for example, I'll take then. Let me just clear that out. I'll create a date. So these are my points up to 200. I say, okay, from, let's say now I want to go from 200 to 2000, and maybe I want 50 points in that range. Okay, it's going to generate all of those points. And all the while, I'm hoping that they're in the right pore size range. From 2,000, I might go up to 60,000 and select 100 points. And these are just examples. Okay. And these are all the points. Okay. And then I can do the same for extrusion. If I'd selected it by pore diameter, now it shows me the pore diameters in nanometers. This is the pore size in nanometers. So those pressure points correspond to those diameters, and you can select the pressure points by pore size as well. So if you know the pore size of interest, you would do this. Okay, either way is acceptable. Okay, and that's what you do if you're selecting stepwise mode. But you have to know something about your sample. Okay, and that really is all there is to it. Okay, in order for setting up the analysis, it's very simple, especially when you save the parameters and all you're adjusting is the sample information, the sample weight, and sample description. So let's just have a quick look at a pore size analysis. Let's just let me just find. Let me go back. Let me do this one. Okay. So now we have a data file loaded here. So this is basically the raw data. Intrusion, extrusion, you can see hysteresis here. Pressure along the bottom, I have it in kilopascals. We can change that to PSI if you like. Now we're looking at PSI or kilopascals. This is the raw volume. So this is basically the raw data. I can see a table of that. Oh, that's the extrusion data. Tables by volume. So we can see the data here in tabular format if you like to look at numbers. And then the most important thing we really want to look at is the pore size distribution normally. So this is normalized volume, that's cc's per gram. Okay, we can look at what's called the cumulative plot. So it's going to look like this raw data, you know, it'll start at 0 and go up to some value against pore size. And so now this axis has been converted to pore size. Okay, so it's the same data in both windows, right? I can put them on top of each other, or I can put them side by side. Okay, so this is the volume pressure data on a linear scale. This is normalized volume. So now this is cc's per gram versus pore diameter on a logarithmic scale. And here you can see there's a little bit of sort of filling up here. There's a significant pore distribution here, and there's another small pore distribution up here. And you can see the hysteresis here, and you can see the entrapment here. Okay. So then what we want to do is maybe look at the pore size distribution. The one that we normally look at is the DVD log, again by pore size. So this is the pore size distribution with very high resolution. We can choose not to see the extrusion. We're just focusing on the intrusion. Okay. We can do some smoothing if we're into such things. Okay, so we can smooth the data. And this is our pore size distribution. The important sort of statistical values here are mode, median, and mean. And we can see that here in the standard report summary. Down here, the software calculates the mean, the mode. The mode is the one that we usually go for, sometimes the median. The mode is this mode here, the most common one. The median obviously is the 50%. And the diameter that we're looking at here is this one here. So in this particular sample, it's 13.34 nanometers is the mode here. Okay, so lots of tables, lots of graphs that you can generate from this in terms of whatever it is that you like to to see. So everything that you see here is pretty adjustable. How you look at the data, you know, obviously all the colors and the markers and so on. If you want to zoom in to show you some software features, you can zoom in. But here you can see the data point resolution is absolutely phenomenal in this auto speed range. Absolutely phenomenal data point resolution. Okay, so that's during the active phase of intrusion. That's up in this part of the plot. You can see the data point resolution here. Absolutely phenomenal. Okay, so that was just a quick overview of the software and the capabilities to get to what we ultimately like to look at, which is the pore size distribution. We can see it in cumulative and in derivative formats. I'm just going to minimize that down and go back to my presentation, and hopefully you can still see this, because what I want to do now is to look at some customer examples rather than looking at some of my files. We can look at what some of our customers have been running. Now these samples were run on a Poremaster 33 GT instrument. So this instrument only had the maximum capable pressure of 33,000 psi. But this is interesting because they have pore size distributions clearly replotted, not in our software, but they've taken the raw data results and have plotted it up in something. I don't know whether it's Excel or something like that. But these pore, so you can see here they call it pore throat size distributions, because remember the mercury has to penetrate through throat pores. So here they've compared and contrasted as part of this data a chalk, a Berea, and a green sand, and obviously very distinctive characteristic pore size distributions for that. A next example here shows on the left here, this is the intrusion extrusion data. Okay, so increasing pressure, this is on a log scale, and here everything's been normalized here. Okay, so it's going up, intruding and extruding. You can see like how much entrapment are in these samples. Huge amount of entrapment in these particular samples. Okay, and from these intrusion curves, then the pore size distributions have been calculated. Okay, and they've got some other Klinkenberg numbers there, but obviously, one family, another family. Don't forget, these are normalized, so they will all look sort of pretty similar in total volume and so on, percentage wise. So you can compare and contrast quite easily samples like this. The third example I have shows some work where the intrusion extrusion is being modeled, mathematically modeled as well, to understand the origins of hysteresis, for example. And if you're into this sort of level of detail, it's quite interesting to look at complete intrusion extrusion curves. Okay, so this can be done on regions without entrapment, for example, and this is where you would use that repeat run feature. You would normally only see entrapment on the first run. Intrude, extrude, you've got entrapment. On the second intrusion, extrusion, normally you'd get no more entrapment. So you can look at a complete cycle without entrapment. That's the second time around. Okay, so you can look at different parts of the pore structure, but also what has been done here is partial intrusion extrusion. So not completely intrude all of the pore structure and extrude from it, but if you more clearly seen on the right hand side, intrude, you can intrude all the way up and extrude. Okay, intrusion, extrusion, or here they call it retraction. Okay, but you can also intrude only to this point. Okay, set a different end pressure and depressurize from there, and you get a different depressurization curve. So you can get insight into the pore structure by intruding only partly or completely or anything in between. Okay, so if you're into sort of complex modeling, you can do a lot of interesting work by changing the pressure at which you end the intrusion and start to come back out. So obviously the normal way to do this, you could intrude up to, you know, this pressure, come back down, go a little bit higher, come back down, go a little bit higher, come back down, and so on. And each run in the system, you can do one automatic rerun, but if you leave the sample in there, okay, and just run it again, you can do another two, okay, or do it again. You can get as many back to back going to different pressures, you know, first one, second one, third one, so on. Okay, let's see example number 4. Just some different samples. These are shales, and I show this, basically it's a fracking. So basically they fracked the shale in the lab by doing the CO2, what they call huff and puff. So pressurize the CO2, let the pressure down and fracture that way. So a sort of an explosive decompression. And you can see, hopefully, that the befores and afters on these in terms of the change in the pore size distribution. So this is obvious here. This one, the number 2, before and after. Okay, so you can, so you can see some. Sorry about that. You can see some differences, and everything before and after measured by mercury intrusion. This is all Poremaster data. And then these are shales with various total organic content on them. And you can see, unfortunately, this is not cumulative, but nevertheless, these are the overlays of the derivatives. And you can see while the pore size distribution is largely the same, maybe this middle one is a little bit different here, but there are some small pores to the left, large pores to the right. There's some larger pores over here, a little bit shifted here, but you can see how the area under the curve, the intrudable volume for this low total organic content is higher than, excuse me, the accessible pore volume for the ones with the higher total organic content, which you might expect that with more organic in the pores, there's less access, less pore volume accessible for mercury. So I've got these 4 examples from the literature, the different instruments used. Poremaster 33 GT, so this could only go up to 33,000, and then the others are Poremaster 60s up to 60,000 psi. And so I would just like to review then what I covered today is basically, you know, what is the Poremaster safe high pressure mercury intrusion porosimetry with instrument features like the macro cell and the repeat analysis and the automatic refill of the capillary after the low pressure, suitable for reservoir rock samples. We can accommodate, as I said, cores. We can accommodate cuttings, for example, or you can break your cores down to use less mercury. Always be aware of, you know, less mercury is good for the environment, and demonstrated some of the software capabilities and a few of our customers' examples. And so I do want to have time for questions, obviously, but I did want to just add a quick word about barite and drilling mud, because I think you've already heard about maybe rheology of these things, and it's just something else that we do at Anton Paar Quantitech here is measuring the density of solids like barite and other solids, you know, calcium carbonate, iron oxides, and other, let's say, diluents, and also the muds themselves. So formulating muds and also cement for well cement for cementing up the borehole. We have gas picnometers to measure the density of these materials using dry gas. Simple gas picnometers called the UltraPic, and it's a single station density picnometer using gas displacement technique. So it's not a liquid displacement technique. So if if you're interested in cements, for example, it's none of these organic solvents. It's not kerosene. Electronic, automatic, accommodates. You can do cores on here. You can get core porosity if you know the diameter of your core. You can do core porosity on here. That it can use nitrogen or helium. Like I say, it will work with dry powders. So all of your formulating solids, perfectly good for. It has one of the 5000 instrument has a mode we call powder protect to stop powder elutration. That's loss of powder into the instrument. So they're designed to work with very fine powders, but at the same time, well, not at the same time, but next analysis, you could just as easily be analyzing oil-based formulations or water-based formulations. Doesn't matter to this instrument. And you can actually use the density as measured by these instruments to calculate percent solids, for example. So you can use it for pre-formulation or post-formulation. So I just wanted just to take a couple of minutes for that, and I appreciate your patience. And with that, I'd like to end the presentation with a huge thank you for your time and interest and attention. And if we do have some questions, I will be happy to answer them to the best of my ability. Let me just show the conversations. I don't know. I'll ask Mohammed if there are any questions.
Yes, I have one question.
Yep.
Regarding to the switch from the low pressure to the high pressure mode with the porosity meter.
Yeah.
Is we need a special tool to transfer the cell from
No.
the low pressure to the high pressure?
No.
Is
No.
there okay? Is there any hazardous precaution for this required?
The at that point, when you take the penetrometer out of the low pressure station, okay, the operator should insert a we call it a blanking rod, but it basically closes off the low pressure station so that there's no chance of mercury vapor coming back out of the low pressure station. Don't forget, it's sort of well enclosed, sort of the cabinet surrounds it, and with the fan running, it should be pulling air through. But when the penetrometer cell is taken from the low pressure station, there's mercury in the capillary. So there's a meniscus, which at that point is exposed. There's a tiny meniscus exposed. At that point, what the operator should do, say, well, what am I going to do about this potential? I mean, it's a tiny amount of mercury that's exposed, but still, you say we want to stop that mercury vapor potentially escaping. So all we have to do, and we supply a small syringe, is take a small amount of the hydraulic oil from a beaker and just put, it's like 100 not even 100 microliters, 50 microliters of oil on that mercury, and that stops the mercury vapor completely from the penetrometer. And then basically, so there's no special tool per se, but we do recommend that a little bit of oil is just put on top of the mercury inside the capillary. That helps get air out of the system when it's in the high pressure system, but it also stops the mercury from potentially evaporating. I mean, mercury has a very low vapor pressure. I don't want anybody to panic about it, but it does mean that after low pressure, you put some oil on, and you can see exactly where the mercury is in the capillary. You know, is it 1 centimeter down? Is it 4 centimeters down? You put some oil in there, and you can set it aside. Now it's completely safe to leave until you're ready to put it into the high pressure. Let's say the previous high pressure hasn't finished. You can just set it aside. It's perfectly safe. And when the high pressure is finished, the system will come back to atmospheric pressure. You open up the high pressure cavity. You take the old sample out. Let the oil drain. Let the oil drain off. Use paper towels and gloves always, and then put the new sample in. But there's no tool to install it into the high pressure. You're basically just moving the penetrometer assembly, as we call it now, because it has the metal cap on it and the two plastic pieces. we put then we put it in the high pressure chamber and put the metal cover over it. It's called a sheath, that metal cylinder on the outside. Pull the sealing plug down, spin it around. All it takes is fingers just to spin it down, tighten it up. No special tools. No.
Yeah.
It's very simple and straightforward.
Yeah. So after complete the test, how to clean the cell? Is there any
Yeah,
remains of mercury will be made?
yes. So you could say the job is half done when we've done the analysis. Now we have to be responsible how we clean up.
Yes.
So the first step is always to work very close to a fume hood, and always move your penetrometers from the instrument to the fume hood in, let's say, an external container, say, a plastic dish or something. Once it's in the fume hood, just briefly, the steps are, rinse it down with a little bit of alcohol. That will take the oil off. The oil that we use mixes very well with isopropyl alcohol. Okay, rinse that down, and then you take the electrode cap off and let the mercury drain from the capillary end through some sort of gauze filter, into a container. Now, normally mercury comes in small plastic bottles. So when you've poured the mercury into the instrument reservoir, you have some empty plastic bottles. So you can recover the liquid mercury back into that bottle, okay? But you're going to empty, and then you're going to empty the penetrometer through some filter. What you want to do is catch the sample, okay? You don't want your sample to be in your mercury bottle. You want your sample. Now, if it's a core sample, that's really easy, right? You can just pick it out. If they're small pieces, you might have to go through a filter, okay, just to catch them. You do another rinse down with alcohol, and then you basically rinse down your sample with alcohol. So I've just got to just bear with me 1 second while I minimize the screen, and then because I have to go shortly, unfortunately. Then you wash down the sample, recover the sample. Now that sample will have mercury inside of it. Okay, we can't prevent that completely. So what we have to do then is store that safely, okay, in a closed container in the fume hood. And when a reasonable amount has been accumulated, then we have to contact a waste disposal company that handles hazardous waste and have them dispose of it responsibly. Now, the liquid mercury that you separated off originally, that can go back to a recycling company. So there are recycle companies who will gladly take the mercury back. It has a very high scrap value, and recycle it for you. So So we have to make sure that mercury doesn't get into the environment, but it is a concern. So anybody who wants detailed stepwise instructions, for example, as to what we do here exactly at Anton Paar Quantitech, stepwise, maybe they could reach out to you, Mohammed, and then you can email me, and I'll be happy to answer those questions.
Thank
Thank you,
you very
Thomas.
much. Thank you very much, Dr. Thomas.
Okay.
We really appreciate your time and effort giving us this interesting and informative session.
Yep.
Now we come to the end of today's session. I'm sorry if any participant have any question, you can WhatsApp me or send an email to me, and I will for sure handle it and forward to Dr. Thomas and answer later. Now we're going to the end of our session, and thank you so much for participating. Thank you again, Dr. Thomas, for this interesting session.
Yeah, well, thank you very much, and thank you for everybody's attention, patience. I wish you a good day, a safe day, and best of health to everyone.
Thank you so much. And you too.
Thank you. Bye-bye.
Bye bye.